Okay, welcome back. This is part 7. So we went through question 17 last time. Here's question 18, and it's also on materials. So it says, some spiders form silk in long, thin threads to catch flying insects. A specific type of spider called the Darwin's bark spider can produce very long threads. A scientist investigated the properties of these threads. Okay, so that's the scenario. It says the scientist applied forces to stretch threads of spider silk. The stress in one thread was 4.3 megapascals, which is 4.3 times 10 to the 6 pascals, because mega is 10 to the 6. That's the first thing you need to check. The radius is given, very thin indeed, a micrometer or two, yeah. And then you use the radius to work out the area, cross-sectional area, because we need that to be able to calculate the force. We've been given the stress, and we want to calculate the force, and we are using the stress equation, which is stress equals force over area. You should then change it to force equals stress times area. So we need the area first, and it's just pi r squared. You put the value of area that you calculate here, so you get 1 mark for doing the area, and then once you've got that, you put the stress that's given in the question above. Yeah, so the stress is given here, and you worked out the area, multiply those two together, and you've to three significant figures, you get 4.88 times 10 to the minus 5 newtons. And you should really round it up to 2 significant figures, because the data provided is provided to 2 significant figures. Okay, so that's the first part, checking that you know how to use the stress equals force over area equation. The second part of the question then goes into the continuation of the science investigation. The scientists investigated a thread of length 25 meters. So the original length was 25 meters. So we know that. So they want you to determine the length of the thread when it was stretched to its limit of proportionality. Well, we don't know what the limit of proportionality is, except they tell us the stress at the limit of proportionality is 300 megapascals, which is 300 times 10 to the 6. They then give us the Young modulus for the spider silk. Therefore, you have the Young's modulus and you've got the stress. So the thing that's missing is the strain. And obviously we know E and we know stress. So the only one we don't know is strain, which is epsilon. So you make the subject of the equation strain, put the numbers in. Stress divided by Young's modulus is what we've done here. And you end up with an answer to 3 decimal places, 4 significant figures of 3.448 times 10 to the minus 2, no units. Why is it no units? Because it's strain, which is extension divided by length, so 2 lengths divided by each other are dimensionless. It's just a ratio. So you know that this strain is the extension divided by the original length. We were given the original length as 25 meters, so you multiply to, if you want to work out the extension will be equal to the original length times the strain that you got, that we just calculated. So you put the value in that we just calculated up there into the equation, and you find that the extension will be 0.862 meters to 3 significant figures. So you add the extension to the original length, which was 25 meters, to 3 significant figures. Here you got 25.86 to 4 significant figures, round it up to 3 significant figures again, and you get 25.9 meters. That's the length at the limit of proportionality Yeah, so that's the length at the limit of proportionality where the stress was given as 300 megapascals. So they're walking you through this question from the materials section of the course. Part C then gives you data. And in the data, they compared the Young's modulus, and properties of the spider silk and the type of steel. Okay, so you can see the Young's modulus, steel has a larger Young's modulus, and they've compared the stress at the limit of proportionality. So at the limit of proportionality, where it stops being a straight line, basically, stress against strain, it was 300 that we looked at for the spider silk, and for steel it's slightly more, 350. Okay, so we've got to use this information. It then says the sketch graph shows the stress-strain relationship for the spider silk. So that's the line they've drawn, up to its limit of proportionality, which we just spoken about. Up to the limit of proportionality. Okay, so we're using the information in the table. So over here would be 300 megapascals. Okay, this bit. Here will be 300 megapascals for the silk. And now they say add a line to underneath the graph, add a line to the graph to show the stress-strain relationship for steel up to its limit of proportionality. So its limit of proportionality is 350, so therefore this peak, the maximum point of the stress here, should be slightly higher than the 300. It's a sketch, so it doesn't need to be 100% accurate. And the other thing is, it's going to be much steeper because the Young's modulus is the gradient of a stress-strain graph. So you've got a stress-strain graph, and the gradient of that is Young's modulus. So you can see the Young's modulus is 200 compared to 8.7. So I've worked out that should be about 23 times steeper. Now, they're not going to look at that, but they want you to show that the steepness is going to be greater, and you have to obviously draw them both starting at the origin, okay? Because when the stress is 0, the strain will be 0. All right, so that's a nice 2 marks, easy, as long as you've interpreted the data given above the graph correctly. A sample of steel has the same shape, length, and cross-sectional area as a sample of silk. So all these are basically making sure that you're doing a fair comparison. Each sample is stretched to its limit of proportionality, in other words, up to the point where it's still a straight line graph. And then explain which sample has the greater elastic strain energy. So elastic strain energy is equal to half Fx, as we did in the bungee jumping question. But we haven't got force extension graph. We've got a stress-strain graph. Well, if the length, the cross-sectional area are the same, then the stress-strain graph, the area underneath it, will be proportional to the elastic strain energy, won't it? So if you think about this, the cross-sectional area is the same for both. Therefore, the force will be proportional to the stress, and the strain, since the lengths are the same for both, then the strain will be proportional to the extension. So you can almost replace, you'll get the same comparison steepness for F against X as you would stress against strain. So the force extension graph will be the same because the dimensions of both samples are the same length and the same cross-sectional area. So you can effectively, you can change stress on that sketch you can change it to, you can put this as a force, and you can put this as an extension. Yeah, and that will be a valid graph. If you did force against extension, it'll be exactly the same shape as you've drawn above. Okay, so force is proportional to stress, and strain is proportional to extension. Okay, it's a little bit messy, but you get my point. Okay, so stress is proportional to extension. Hope that makes sense. So basically you could just replace force, stress, and strain and put force against extension. You have exactly the same comparison of lines on them. Okay. Now the strain energy then is half Fx, and if the shape of the Fx graph is the same, then the strain energy underneath the steel will be this, and underneath the spider, is it called spider? Under the spider silk. So this will be the silk strain energy, and you can see that it's flatter and wider, whereas the strain energy for the steel is taller and thinner. Okay, so that's basically what they want you to realize. So you've got to say that the elastic strain energy is proportional to the area under each line of the graph, yeah, which it is. And the area under the silk line is actually greater than the steel line. So the silk line has the greater elastic strain energy, yeah? So the elastic strain energy of silk will be greater than for steel, and that's because it can basically extend much longer. So it can take more strain. Make sense? And that's the 12 marks for this question on Young's modulus. A nice question comparing a natural material with man-made steel. So if you found that useful, make sure you give it a like. I'm not getting as many likes as I do for my older students who are doing work for year 13. They're giving me likes in a ratio of about 7 views to 1 like, and you lot are watching it and you're not giving a thumbs up, and you're not sharing it as much with your friends possibly, and without that we're not going to get the channel becoming sustainable. So please make sure if you find it useful, if you're watching it and you're finding it useful and you're helping you with your physics, make sure you show your appreciation by giving a like so the channel grows. And if the channel grows, you'll get more videos in the future. And that's basically how YouTube works. Unless you get likes, shares, and more subscribers, the channel basically goes to the bottom of the list. And I think I'm getting quite a lot of positive feedback from the clarity of my explanations. So I think it will help a lot of students if the channel grows this year. My aim is to get to 1,000 subscribers as soon as possible this academic year. We're up to 750 already. So thank you very much if you're a long-time subscriber. And do pass on the channel to, if you've got younger brothers and sisters, cousins, friends who are doing GCSE. The GCSE playlists are newer. Some of them did last year and they've had over 1,000 views. And the record view is an A-level paper for Unit 5. I think we've got over 3,000 views already, so I'm quite pleased with how it's going. But obviously with the new students coming in each year and the old ones now having gone to university, we need to keep that passing on of the baton from one year to the next. So you pass it on to people who are coming into A-level or people who are doing GCSE, so the channel gets better views, greater views. So thanks very much for watching. Hopefully see you in the next video with lots of likes. Hit that like button. Thank you.